Okay, this is the third video for 5.4, applying quantum mechanics to electrons in atoms, and we're going to talk about electron configurations for ions. So if I'm taking a look at the S negative 2 ion, what that negative 2 means is that you gained 2 electrons. And so if we gain 2 electrons and we take a look at the periodic table here, that means you move forward 2 boxes and you're going to write the electron configuration for argon. You don't become argon, you just have the same number of electrons as argon, which would be 18. So you'll notice this means you will have 1s2, 2s2, 2p6, 3s2, 3p6 as your electron configuration. If you wanted to write the shorthand notation would be argon in a bracket. Now, if I'm looking for another ion that has the same electron configuration as S negative 2, I would look at something like Cl negative 1. And the reason I would look at Cl negative 1 is because chlorine is right here. The negative 1 means it gained an electron, so now it has the same number of electrons as argon, so they both have 18. So if these both have 18 electrons, we say they are isoelectronic with each other. And this is a term defined in the text. Okay? If I am looking at some other ions, for instance, I'm looking at something in the middle. Let's say I'm looking at an Sn plus 4. If I'm looking at Sn plus 4, that's a transition metal. And Sn plus 4, if I go back to the periodic table, you'll notice that neutral 10 is right here. And you would expect neutral 10 to have a configuration of, I'm going to do the abbreviated configuration, Kr in a bracket, followed by, this is 1, 2, 3, 4, 5. This is 5s, 2. This is the beginning of 4d, 10. And then this is the beginning of 5p, and we end on 5p2. Okay? So if in the event you have Sn plus 4, this plus 4 means I lost 4 electrons. Okay? So if I lost 4 electrons, what you're going to do is you're going to remove the electrons from the higher energy levels first so that you can end up with the proper electron configuration. So here, they've told you that you're going to remove the 4 outermost electrons to get the configuration for Sn plus 4. The outermost electrons are going to be the electrons that are in the 5s and the 5p because of the number 5. So you're going to remove these electrons and these electrons, which is going to leave you with Kr in a bracket followed by 4d10. So these are now gone. Okay? Now, there are a couple of other things to mention. Those things are exceptions. I'm going to put these elements in a bracket. It's chromium and molybdenum and copper and silver and gold. You'll notice if you're looking at the periodic table, they have a unique location. Here's chromium and molybdenum here. Here's copper, silver, and gold. You'll notice chromium and molybdenum are 1, 2, 3, 4 boxes in on the Ds. then you'll notice copper, silver, and gold are 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes in to the Ds. What does that mean? When you're writing the electron configuration for chromium or molybdenum, you would expect it to be 4s2 and then 4d4, but it's not. An electron will jump over from 4s and it will half fill the 3d because it's more energetically favorable for that to happen. The same thing will happen with molybdenum. For molybdenum, you would expect 5s2, 4d4, but an electron jumps over from 5s and half fills the 4d. So it's really 5d1, 4d5. If I'm talking about copper, silver, or gold, you would expect these to end on a D9, but what really happens is an electron jumps over from the S and completely fills the D, so you actually end on D10 for all three of these. So I'm going to write out those configurations for you here. So for chromium and molybdenum, chromium and molybdenum are 4N. So chromium is going to be argon in a bracket. This is the shorthand, followed by 4s1, 3d5. This is the real configuration for chromium, okay? And that's because you've got an electron in 4s jumping over to half fill the 3d and give you this. For molybdenum, that one is going to be Kr in a bracket, followed by 5s1, 4d5, okay? If I'm looking at copper, silver, or gold, those are the ones that are going to end on a D10. So for instance, silver, you would expect to be Kr in a bracket, followed by 5s2, 4d9. But an electron jumps over from the 5s, and it's going to completely fill the Ds. So you get Kr in a bracket, 5s1, 4d10. So this is the real configuration for silver. The same thing would apply for copper. Copper would end on 4s1, 3d10. And if you're looking at gold, it would do something similar as well.